Welcome to our problem-solving session. Today, we'll dive into problem number 42, Trapping Rainwater, a classic algorithmic challenge that tests your problem-solving and optimization skills. Let's preview the problem and explore the approaches to solve it. The problem we're solving is called trapping rainwater. Imagine an elevation map represented by an array of non-negative integers, where each value corresponds to the height of the terrain at that index. The width of each bar in the elevation map is 1 unit. After it rains, water gets trapped in the valleys formed by the bars. Our task is to calculate the total amount of water that can be trapped. The input is an array called height, which contains the heights of the bars. The output is a single integer that represents the total units of trapped water. For instance, if the input array is 0102101322121, the output is 6 because that's the total amount of water trapped between the bars in this elevation map. To understand how the water is trapped, let's break it down. In the first example, at index 2, there's 1 unit of water trapped between the bars of height 1 and 2. At index 5, there are 2 units of water trapped between the bars of height 2 and 3. At index 8, 1 unit of water is trapped, and at index 10, another 2 units are trapped. When we add these values together, the total trapped water is 1 plus 2 plus 1 plus 2 equals 6. Now, in a second example with the input, for 20325, the output is 9. Here, we find that there are 2 units of water at index 1, 4 units at index 2, and 3 units at index 4. The sum, 2 plus 4 plus 3, gives us the total of 9 units of trapped water. The second example illustrates a larger elevation map where the total trapped water is 9 units. Moving on to the third example, we have an input of 1, 0, 2. In this case, there's 1 unit of water trapped at index 1, which is the valley between the bars of height 1 and 2. The total trapped water here is simply 1. Finally, we have some constraints to consider. The length of the height array is n, where 0 equals n equals 100, 0, 0, 0. Each value in the array falls within the range of 0 to 10, 0, 0, 0. These constraints ensure that the problem can handle very large inputs efficiently. Now, let's discuss a few edge cases that are important to keep in mind. If the array is empty, meaning n equals 0, no water can be trapped, so the result is 0. Similarly, if all the bars have a height of 0, there's no elevation difference to trap water, so the output is also 0. If there are fewer than 3 bars in the elevation map, trapping water is not possible, and the result will again be 0. Lastly, if all the bars are of the same height, no valleys can form, meaning no water can be trapped, leading to an output of 0. These edge cases highlight the scenarios where trapping rainwater is either unnecessary or impossible. To solve the trapping rainwater problem, we first considered the brute force approach. The intuition here is to calculate the maximum height of bars to the left and right of each index I. Using these values, the water trapped at index I can be determined by taking the difference between the smaller of these 2 maximum heights and the height at I. The steps involve iterating through each index, finding the maximum height to the left and to the right, and then calculating the trapped water at that index. By summing up the trapped water for all indices, we obtain the total water trapped. While this approach is straightforward, its time complexity is n squared, due to the repeated calculations of left_max and right_max for each index. However, it uses O(1) space since no additional data structures are required. The brute force approach, though simple, has a significant drawback: it performs redundant computations for overlapping indices, making it inefficient for larger inputs. To address this, we considered an optimized approach using the 2-pointer technique. This method eliminates redundancy by utilizing 2 pointers, left and right, which start at the beginning and end of the array, respectively. As we traverse the elevation map, we maintain 2 variables, left_max and right_max, to store the maximum heights encountered so far from the left and right. Depending on the current heights at the left and right pointers, we either update these maximums or calculate the water trapped. This approach continues until the 2 pointers meet, ensuring that each index is processed at most once. The total trapped water is then returned. The optimized 2-pointer technique offers a time complexity of n, since each index is visited only once during the traversal. It also has a space complexity of O(1), as it requires only a few variables to keep track of the pointers and maximum heights. This makes it significantly more efficient than the brute force approach. However, it is slightly more complex to implement due to the need for conditional checks in managing two pointers. Another approach we considered was the dynamic programming method. This approach pre-computes the left_max and right_max arrays to avoid repeatedly recalculating them. By storing these values in advance, the calculation of trapped water for each index becomes more efficient, as we can simply look up the pre-computed values instead of recalculating them. In terms of complexity, the dynamic programming approach achieves a time complexity of O(n), as it involves a single traversal to pre-compute the left_max and right_max arrays, followed by another traversal to calculate the trapped water. However, it uses O(n) space due to the additional arrays. While faster than the brute force approach, the dynamic programming method's space requirement can be a drawback for large input sizes. On the other hand, it is simpler to implement compared to the two-pointer technique since it avoids the need for conditional checks in pointer manipulation. This trade-off highlights the importance of balancing time and space complexity when selecting the most suitable approach. Ultimately, we chose the optimized two-pointer technique as our final strategy due to its balance of efficiency and space optimization. While the dynamic programming approach achieves comparable time complexity, the two-pointer technique reduces space usage from O(n) to O(1), which is especially critical for handling large inputs. This method also avoids the overhead of pre-computing arrays, making the process more streamlined. The key insight here is that we don't need to know the exact left_max and right_max values for all indices in advance. Instead, we can calculate and update them dynamically as we traverse the elevation map from both ends. This realization eliminates the need for auxiliary arrays and ensures a single-pass solution. Although the brute force approach is easy to understand, its inefficiency renders it impractical for larger inputs. By choosing the two-pointer technique, we achieve an optimal balance with O(n) time and O(1) space complexity. To begin solving the trapping rainwater problem using the brute force approach, we first initialize a variable called total_water to 0. This variable will accumulate the total amount of water trapped as we process the array. Next, we iterate over each bar in the height array, starting from the first bar and ending at the last, but skipping the edges since water cannot be trapped at the boundaries. For each bar at index I, we need to calculate two key values. The first is left_max, the maximum height among all bars to the left of the current index. To find this, we examine the subarray from the start of the array up to I1 and determine the largest bar height. This value represents the highest boundary on the left side of the current bar. Now, we turn our attention to the right side of the current bar. For index I, we calculate right_max, which is the maximum height among all bars to the right of the current index. This is done by examining the subarray from I+1 to the end of the array and identifying the tallest bar in that range. Once we have both left_max and right_max, we can calculate the amount of water trapped at the current bar. This is determined using the formula min, left_max, right_max, height, I. If the result is positive, it means water can be trapped at this bar, and we add the value to total_water. If the result is 0 or negative, no water is trapped, and we move on to the next bar. These calculations are repeated for every bar in the array, excluding the edges. Finally, after processing all the bars, the value of total_water is returned as the total amount of water trapped. The key to understanding this approach lies in the role of left_max and right_max. Water trapped at a bar depends on the shorter of the tallest bars on its left and right. This ensures that water is contained within the boundaries set by these two heights. There are several edge cases to consider. For instance, if the height array is empty or contains fewer than 3 bars, it is impossible to trap any water, so we immediately return 0. Similarly, if all the bars in the array are of equal height, no water can be trapped. It is also important to test the algorithm with arrays that form valleys of varying depths to ensure the logic is robust. While the brute force approach is straightforward and systematically processes the array, it has a high time complexity of O(n²) due to the nested iterations required to compute left_max and right_max for each bar. The brute force approach relies on a few specific data structures and operations. The input is provided as an array called height, which stores the heights of the bars. We use variables such as left_max and right_max to store the tallest bars to the left and right of the current index, and the variable total_water is used to accumulate the total amount of water trapped throughout the process. The most computationally expensive operation is finding the maximum heights, as determining left_max and right_max requires iterating through subarrays for every bar. This repeated iteration is what contributes to the O(n)² time complexity. On the other hand, the water calculation itself, using the formula min, left_max, right_max, height, I, is efficient and represents the core logic that ensures trapped water is only calculated when taller bars exist on both sides of the current bar. To optimize the solution, we can significantly reduce the time complexity by pre-computing the left_max and right_max values for all indices in advance. Using dynamic programming, we can store these maximum heights in arrays, avoiding the need to repeatedly iterate through subarrays. This approach improves the time complexity to O(n). Alternatively, we can achieve the same efficiency with constant space using a two-pointer technique. By maintaining pointers at both ends of the array and iteratively calculating maximums as we move inward, we can simultaneously compute the trapped water while minimizing memory usage. These optimizations make the algorithm much more efficient and suitable for larger input sizes, addressing the primary drawback of the brute force approach. This implementation solves the trapping rainwater problem using the dynamic programming approach with two auxiliary arrays. First, we check if the input array height has fewer than 3 elements, as no water can be trapped in such cases. If it's valid, we initialize two arrays, left_max and right_max, to store the maximum height to the left and right of each bar, respectively. We then populate the left_max array by iterating from left to right. At each index I, we store the maximum of the previous left_max value and the current height. Next, we populate the right_max array by iterating from right to left, storing the maximum of the next right_max value and the current height. Finally, we calculate the trapped water by iterating through the height array. At each index, the trapped water is determined by subtracting the height of the current bar from the minimum of left_max and right_max at that position. This ensures that only valid water levels are included, and negative values are avoided using max 0. The total trapped water is accumulated in the variable total_water, which is returned as the result. The time complexity is O(n) due to the 3 linear traversals of the array, and the space complexity is O(n) due to the 2 auxiliary arrays. Here, we are implementing the solution to the trapping rainwater problem in Java. The method trap takes an integer array height as input, which represents the elevation map. First, we perform a basic validation to ensure the input is not null and has at least 3 elements, as trapping water requires at least 3 bars. If this condition is not met, the function returns 0 immediately. Next, we initialize the size of the array, n, and create 2 auxiliary arrays, leftmax and rightmax. These will store the maximum heights encountered from the left and the right for each position in the elevation map. The leftmax array is built starting from the first index. The first element is initialized to height 0, as it has no bars to its left. Then, for each subsequent bar, the value at leftmax, I, is set to the maximum of the previous maximum, leftmax, id1, and the current bar height, height, I. Similarly, the rightmax array is constructed, but this time starting from the last index. The last element is set to height, n1, and for each position moving backward, rightmax, I, is updated to the maximum of rightmax, I plus 1, and height, I. These arrays effectively capture the tallest bar heights on both sides of each position, which are critical for calculating trapped water. With the leftmax and rightmax arrays built, we can now compute the total amount of trapped water. We initialize a variable, total water, to 0. Then, we iterate through the elevation map from the second position to the second to last position. For each bar, the water it can trap is determined by finding the minimum of the left and right maximum heights for that position, subtracting the bar's height, and taking the maximum of this resultant 0 to ensure no negative values. This value is added to total water. Once the loop completes, total water holds the total volume of water trapped across the elevation map. Finally, we return this result. This implementation efficiently calculates the trapped water in O(n) time, as the left and right maximum arrays are built in linear time, and the final calculation loop is also linear. To solve the problem of trapping rainwater, we start by initializing a few key variables. First, we determine the length of the input array, which is 12 in this example. Then, we create two arrays, left_max and right_max, each initialized with zeros and having the same length as the input array. These arrays will help us keep track of the maximum height of the barriers to the left and right of each index. Additionally, we initialize a variable total_water to 0, which will store the accumulated amount of trapped water. Next, we build the left_max array. This array keeps track of the highest barrier encountered so far as we iterate from left to right. For example, at index 1, the maximum height between left_max 0 and height 1 is calculated as 1. Similarly, at index 2, the maximum between left_max 1 and height 2 is also 1. This process continues for each index until we complete the array, which results in the final left_max array 0, 1, 1, 2, 2, 2, 2, 3, 3, 3, 3, 3. This array will now help us calculate the trapped water at each position in the next steps. Now, we construct the right_max array. This array captures the highest barrier encountered so far as we move from right to left. We start by setting right_max 11 to the height at the last index, which is 1. At index 10, the maximum value between right_max 11 and height 10 is calculated as 2. Similarly, at index 9, the maximum between right_max 10 and height 9 remains 2. This process continues for all indices, resulting in the final right_max array 3, 3, 3, 3, 3, 3, 3, 3, 2, 2, 2, 1. With both left_max and right_max arrays ready, we can now calculate the trapped water at each index. For indices where water can be trapped, we find the minimum of the values in left_max and right_max, then subtract the height at that index. For example, at index 1, the minimum of left_max 1 and right_max 1 is 1, and subtracting height 1 gives 0. At index 2, the calculation yields 1 unit of trapped water. Repeating this for all indices from 1 to 10 and summing the results gives a total trapped water of 6 units. This is our final output for the first example. In this example, the input array is smaller, with a length of 6. We begin by initializing the variables, left_max and right_max arrays filled with zeros, and total_water set to 0. The process to build the left_max array is similar to the previous example. We start by setting left_max 0 to the height at the first index, which is 4. Then, for each subsequent index, we calculate the maximum value between the current height and the previous value in left_max. For instance, at index 1, the maximum of left_max 0 and height 1 is 4, and at index 2, the maximum remains 4. This continues until the last index, resulting in the final left_max array 4, 4, 4, 4, 4, 5. With this array, we now have the maximum heights to the left of each index, which will be used in the calculation of trapped water. Next, we build the right_max array for this example. Starting at the last index, we set right_max 5 to the height at index 5, which is 5. Then, for each preceding index, we calculate the maximum value between the current height and the next value in right_max. For example, at index 4, the maximum between right_max 5 and height 4 is 5, and at index 3, the maximum remains 5. This process is repeated until the first index, resulting in the final right_max array 5, 5, 5, 5, 5, 5. With both the left_max and right_max arrays constructed, we compute the trapped water at each index. For instance, at I = 1, the minimum of left_max 1 and right_max 1 is 4, and subtracting height 1 gives 2 units of water. At I = 2, the calculation yields 4 units, and at I = 3, it gives 1 unit. Summing the trapped water from indices 1 to 4 results in a total of 9 units, which is the output for this example. In this final example, the input array consists entirely of zeros, meaning there are no barriers to trap any water. When there are no walls present, it is impossible for water to be retained. Hence, the total trapped water in this case is simply zero. This demonstrates that the algorithm correctly handles edge cases where no water can be trapped. The time complexity of this algorithm can be broken down into three key steps. First, we build the left_max array. This is done by iterating through the height array from left to right. At each index I, we calculate the maximum height seen so far on the left, which is stored as left_max I. Since this involves just one pass through the array, it contributes O(n) to the time complexity. Next, we construct the right_max array. This time, we traverse the height array from right to left. For each index I, we calculate the maximum height seen to the right and store it in right_max I. Similar to the previous step, this also requires a single pass, contributing another O(n). Finally, we calculate the amount of water trapped at each index. This involves iterating over the array again, skipping the first and last elements, and using the pre-computed left_max and right_max values to determine the trapped water at each position. This step is also linear, contributing O(n). Together, these three steps result in an overall time complexity of O(n). Now that we've broken down the individual steps, we can conclude that the total time complexity of the algorithm is O(n). Each of the three passes through the height array is linear, so the complexity scales directly with the size of the input. Shifting focus to space complexity, the algorithm requires additional memory for the left_max and right_max arrays. Both of these arrays are the same size as the input height array, meaning they each require O(n) space. Additionally, the algorithm uses a few extra variables, such as n for the size of the input and total_water for keeping track of the result. These variables take constant space, or O(1). Since the space required by the left_max and right_max arrays dominates, the overall space complexity is O(n). To appreciate the efficiency of this optimized solution, let's compare it to the brute force approach. In a naive implementation, for each index I, we would calculate the trapped water by finding the maximum height to the left and right dynamically, using two separate loops. This would result in two nested loops, an outer loop to iterate through the array and two inner loops for finding maximum heights. As a result, the time complexity for the brute force method is O(n²). However, it has a space complexity of O(1), since no extra memory is used. In contrast, the optimized solution avoids nested loops by pre-computing the left_max and right_max arrays. This reduces the time complexity to O(n), though the space complexity increases to O(n), due to the additional arrays. This trade-off makes the optimized approach significantly faster for larger inputs. Analyzing the algorithm further, we see that its time complexity remains O(n) in all cases. In the best-case scenario, the algorithm still performs 3 linear scans of the height array, meaning the number of operations is always proportional to the input size, regardless of the height distribution. Similarly, in the average case, the operations remain linear, as each step is executed in O(n) time. Even in the worst case, the algorithm still processes each element a fixed number of times, maintaining the O(n) time complexity. From a mathematical perspective, the 3 linear scans, one for left_max, one for right_max, and one for calculating trapped water, each take O(n) operations. Adding these together results in O(n) plus O(n) plus O(n), which simplifies to O(n). On the space complexity side, the dominant factor is the storage for the left_max and right_max arrays, each requiring O(n) space, while the additional variables contribute only O(1). This confirms an overall space complexity of O(n). When tackling the trapping rainwater problem, there are several common mistakes to watch out for. One frequent issue arises in the brute force approach, where the left and right maximum heights for each index are computed repeatedly within nested loops. This results in a time complexity of O(n²), which is highly inefficient. To avoid this, you can pre-compute these values once and store them in arrays, reducing redundant calculations. Another mistake is misunderstanding how to calculate the water stored at each index. Remember, the amount of water is determined by the minimum of the left and right maximum heights minus the height of the current bar. If you forget the minimum function or apply it incorrectly, your results will be wrong. Additionally, edge cases are often overlooked. For instance, arrays with fewer than 3 elements cannot trap any water, and failing to check for these cases can lead to runtime errors. Finally, the two-pointer approach, while efficient, is prone to implementation errors. Some might move both pointers simultaneously or fail to properly update the left and right maximums, leading to incorrect results. Be meticulous when handling these details. Lastly, always pay attention to the constraints of the problem. For example, the input will always involve non-negative integers, so there's no need to account for negative or non-integer heights. In interviews, the trapping rainwater problem highlights key problem-solving patterns and trade-offs that are invaluable to understand. A critical takeaway is recognizing the importance of pre-processing arrays or leveraging auxiliary data structures to optimize computations. This pattern is common in dynamic programming and sliding window problems, so mastering it has broader applications. The two-pointer approach stands out as the optimal solution, achieving O(n) time complexity and O(1) space complexity. Interviewers often appreciate when you can articulate why this approach is superior, specifically, how it avoids redundant calculations and minimizes resource usage. Furthermore, you may be asked to discuss trade-offs between different solutions, such as why the two-pointer method is more efficient than using extra space for arrays. Being able to critically evaluate these approaches demonstrates a deeper understanding. Finally, time management is key during an interview. If you find yourself stuck, don't hesitate to start with the brute force solution to establish the logic, but quickly identify its inefficiencies and explain how you'd optimize it step by step. This methodical problem-solving approach is often just as important as the final implementation. This problem is closely related to several other LeetCode challenges, making it a great foundation for tackling similar questions. One prominent example is the container with most water problem, LeetCode number 11. This also uses a two-pointer strategy, but the focus is on maximizing the area between two vertical lines. Another related problem is largest rectangle in histogram, LeetCode number 84, which involves finding the largest rectangle in a bar graph. This is often solved using a monotonic stack, a technique that's also applicable to certain variations of the rainwater problem. For a more advanced challenge, there's Rainwater Trapping 2, LeetCode number 407, which extends the concept to a 2D grid, requiring you to calculate water trapped on a 3D surface. Lastly, Sliding Window Maximum, LeetCode number 239, emphasizes efficient pre-processing to optimize calculations for maximum or minimum values. These problems collectively highlight the importance of dynamic programming, two-pointer techniques, and efficient data structure usage, so practicing them will significantly sharpen your problem-solving skills. There are several approaches to solving the trapping rainwater problem, each with its own trade-offs. The brute force method, though simple to implement, involves nested loops to calculate the left and right maximum heights for every index, resulting in a time complexity of O(n squared). While straightforward, it's not practical for larger datasets. A step up from this is the dynamic programming approach, which precomputes the left and right maximums for all indices and stores them in arrays. This allows you to calculate the trapped water in a single pass, reducing the time complexity to O(n). However, it requires O(n) extra space for the arrays. The two-pointer approach is the optimal solution, achieving O(n) time complexity and O(1) space complexity. By using two pointers to dynamically track the left and right maximums while moving inward, you can efficiently calculate the trapped water. This method, while highly efficient, demands careful handling of pointer movements and updates. Lastly, the monotonic stack approach is another viable O(n) solution. Here, a stack is used to keep track of decreasing bar heights, and water is calculated when taller bars are encountered. This approach is slightly more complex to implement but is particularly useful for problems involving histograms or similar structures. Each method has its strengths, so understanding their trade-offs is crucial both for solving the problem and for interview discussions. Great job following along. We've covered the trapping rainwater problem, discussed key insights, and implemented an efficient solution. Keep practicing, stay curious, and don't hesitate to revisit this challenge to reinforce your understanding. Thanks for watching. and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!